Hi everyone. Today we are beginning a new chapter, and in this chapter we are going to study two new families of functions, and they will actually be our last families of functions for this semester. But before we dig into that, I always find it kind of useful to take a step back for a moment and pause, and let's look at kind of everything that we've studied in terms of functions this semester and try to put them in categories. Because you learn so much in college algebra, it can sort of just float around and we don't have any connections, and I want us to categorize what we've learned so far. So if you'll just think with me briefly before we start this section, I draw a little like umbrellas for families of functions. And what we started with, in the last chapter, I should say, are the polynomial functions. Okay, so remember the polynomial family of functions, they're going to include lines, linear functions, which are degree 1. They're going to include parabolas, which are quadratic functions, which are degree 2. Then we also studied y equals x cubed. That was one of our parent functions. And then in chapter 4, we discovered that those x cubed functions can actually begin to have maximum and minimum values. So those are going to be examples of functions that are degree 3. And then x to the 4th might also look like a u, just like an x squared function, or it may begin to have some peaks and valleys and kind of have more of that W shape. And that's going to be degree 4. And then it can just go higher from there. So if you have a polynomial function, I always say you have whole number exponents. Those degrees are going to be whole numbers in the polynomial family. Then the second half of chapter 4, we moved on to the rational functions. And remember, the root word in the word rational is ratio, because those rational functions are built by putting a polynomial over another polynomial, which means these are the kind of funky functions because they are characterized by often having asymptotes. They don't have to, but many times they do. So vertical, horizontal, or possibly slant asymptotes. So this was the focus for last chapter. Now we have a few functions that we have studied that are kind of outliers. If we go back to the very beginning of the entire semester, another little umbrella. Forgive my lovely umbrellas that kind of look like mushrooms. But we did take a look at some of the radical functions. Remember the square root of x? So square root of x had a shape like that, and the cube root of x as well. Kind of that elongated S shape. And so we often call those radical functions, or you might call them the root functions. So I'll say radicals or root functions are in that function family. And then kind of alone, I guess I would say, we have absolute value. And the reason why it's not really its own category is because this semester the only absolute value curve that we have studied is the absolute value of x. And they get more advanced than that, but for right now, if you want to have it in its own category, you certainly can. So these are kind of the categories of functions that we've studied so far. And then in chapter 5, what we're going to be adding on is another umbrella, and these kind of go together, and they are the exponential functions. So we're going to take a look in chapter 5 at functions that grow exponentially, and then along with that, we will see, I call them their cousins, the logarithmic functions. And so these basic 5 umbrellas summarize all of the types of functions that we have seen so far and will see in college algebra. So let's dig into section 5.1. Before we can talk about exponential and logarithmic functions, we have to do a little bit of background work and discuss what it means to be a one-to-one function. So a function is one-to-one if every element in the range corresponds to only one element in the domain. So again, every element in the range, that means every y value, is going to correspond to only one element in the domain. So every y value corresponds to only one x value. So Previous to this, we have studied functions, and we understand that functions, every element in the domain corresponds to only one element in the range. That's what we actually started our semester with, reviewing functions. So we're adding another layer to that. And now if you could have a function, but it might be a one-to-one function if it fits this definition. And that essentially means that if you have a one-to-one function, it's going to pass both the vertical and the horizontal line tests. So let's look at this visually first, using the first three examples here, A, B, and C. Which of the following represent one-to-one functions? Now, every one of these is a function because they all pass the vertical line test. But you'll notice on example A, if I draw a horizontal line, it's going to intersect this curve 2 places. This means it is going to fail the horizontal line test. So this is not a one-to-one function. So we'll just write not one-to-one. Now let me just show you in a table what that's going to look like. Just pretend, let's say this is an x value of 2, and we'll just say this is a y value of 2 as well, and then an x value of -2, just as an example. So you'll notice when I plug in -2 for x, I get out +2 for y, and when I plug in +2 for x, I also get out +2 for y. So you can see the problem here is this range value of y equals 2, it corresponds to 2 different x values. So that's why this fails to be a one-to-one function. Looking at B, we have the same issue. If I draw a horizontal line, it's going to intersect this curve actually 3 times, and that means it fails the horizontal line test. So this is not one-to-one either. And then our last curve, which, as an example, just for final exam review purposes, this might be like y equals x cubed, but notice the end behavior, it ends pointing down, so this has been reflected. So this might be like y equals -x cubed because of that reflection. And then you'll notice that it's been shifted, so this might be like y equals -x cubed plus 1. However, when I draw horizontal lines, you'll notice that those horizontal lines are all going to intersect the curve just one time, all the way throughout that curve. So this does pass the horizontal line test. So this is a good example of a function that is one-to-one. So now that we have an understanding of what a one-to-one function is, we can move on to inverse functions and put that information together. We'll build on that information. So hopefully you've seen inverse functions in your previous math class, and this is just a review. But just in case, this is our notation for an inverse function. You have this f, and then you see this -1 that's up in a superscript. And what you have to be careful of here, this is pronounced the inverse of f. However, that -1 is not an exponent. So be careful. This is not f to the negative first power. In other words, remember, negative exponents, let me show this off to the side. If we had x to the negative first power, that means it's really the same as 1 over x. That's a property of exponents when the exponent is negative. But we have to be really careful when you see this in function notation that -1 is not an exponent. So this does not mean we're doing 1 over the function f of x. This is actually a new notation that has its own meaning, and that is denoting the inverse of function f of x. So what is an inverse? Well, basically, if a function is a one-to-one function and it contains ordered pairs a, comma, b, then the inverse will contain the points b, comma, a. Now, if the original function had coordinates a, b, and the inverse contains the coordinates BA, then essentially all that we've done is interchange our x and our y values. So it's going to become really simple to find inverses because all you have to do is interchange. Some people say switch or swap. I'm just going to say interchange the x and the y values. So if your function had the coordinate 5, 3, then the inverse would have the coordinate 3, 5. And if we are interchanging the x and y values, then that means that the domain and ranges are going to switch as well. So we say the domain of the original function f of x, that becomes the range of the inverse. So the domain of f of x becomes the range of the inverse. And rather than writing the word inverse, I'm going to go ahead and write the notation. Okay, the domain of f of x becomes the range of the inverse function. And likewise, the range of the original function, f of x, so the range of f of x becomes the domain of the inverse. So essentially, all we're doing is we're swapping or interchanging our x and our y values, and we get a new graph, and that new graph is what we call an inverse. So look at example 2. It contains a total of 4 ordered pairs, and the first question is f of x 1 to 1? So does every y value correspond with only one x value? So you'll look, we have a y value of 2, and we never have a y value of 2 again. And we have a y value of 5, only one time. We have a y value of 4 and a y value of -2. So each of these y values has its own unique x value. So therefore we can say, yes, this is a one-to-one function. Now, if you have a hard time seeing that from the ordered pairs, then I would encourage you to sketch a quick little graph of these 4 coordinates. So if I plot these, and I'm not going to connect these are 4 discrete points, we call this. But once I plot all 4 of those coordinates, then you can see if you did try the horizontal line test and draw a horizontal line, each horizontal line would only intersect one point. So graphically, you can see that yes, this would be a one-to-one function. So finding the inverse is super quick and simple. The inverse of f will just be the set of points where the x and the y values have been interchanged. So instead of -1, 2, we've got 2, -1. And instead of 0, 5, you have 5, 0. And then you'll have 4, 3. And then -2, 4. And we'll use curly brackets to list all 4 of these ordered pairs. So there's your inverse.